You can scan the network to find out the computer systems in a network and discover the network topology. First, let's see the scan types. There are two types of scanning. First type is passive scan. In this type of scanning, you don't want to be recognized by the target. In this regard, you don't directly contact target systems. Just by watching a network's traffic flow, passive scanners can deduce a large amount of information about the communicating systems. You can use tools such as TCP dump or Wireshark to monitor network traffic. Looking at the ARP table in a computer which is connected to the network is another example of passive scanning. So the second type is active scan. In this type of scanning, you scan on the target systems. Active scanning requires more preparation for the attacker or pen tester because it leaves traces, which are likely to alert the target or produce evidence against him. Active scanning on your network can also return great headaches, however. It can have a high political cost and far-reaching effects on system uptime and reliability. If not done carefully, it can be an ineffective, inefficient way to gather information. We'll see Nmap in details. hping is an excellent command line-oriented TCP/IP packet analyzer. It looks like ping command, but hping isn't only able to send ICMP echo requests. It supports TCP, UDP, ICMP, and raw IP protocols, has a traceroute mode, the ability to send files between a covered channel, and many other features. Scapy is a powerful interactive packet manipulation program. It is able to forge or decode packets of a wide number of protocols, send them on the wire, capture them, match requests and replies, and much more. Traceroute is a utility that records the route, the specific gateway computers at each hop through the network between your computer and a specified destination computer, so you can find out the network devices between you and the target and identify the network topology. There's a really good comparison of active and passive scanning on networkworld.com website, which says, just as you can determine the type of cheese by tasting it, an active scan, you can also use passive techniques such as reading the label or smelling the aroma as it passes by. Before talking about using ARP tables for passive scanning, let's talk a little bit about ARP protocol and mechanism first. So, Address Resolution Protocol, ARP, is a network layer protocol used for mapping a network address such as an IPv4 address to a physical address such as a MAC address. To simulate how the ARP mechanism works, we have a small network in the slide, a switch on top, and 3 computers connected to it. Computer A wants to talk to computer C. It puts an ARP request onto the wire, which happens to be broadcast. Essentially what it's saying is, who has computer C's MAC address? Of course, because it's a broadcast, every system on the network hears it. Does everybody respond? Well, what happens is that B hears that A is looking for the MAC address of computer C. B knows that it's not computer C and therefore does not respond to the broadcast. The broadcast, the ARP request, goes out to every system, but the only system that will reply is computer C with an ARP reply. In other words, computer A says, who has the MAC address of computer C? And although all the workstations hear the question, only C replies and says, I've got the MAC address of computer C, and this is what it is. So the ARP reply sends back the MAC address to computer A, and each of these machines start building an ARP table. So what is the ARP table? Since computers cannot send broadcast messages every time they need to connect with another network device, they store the IP addresses and the corresponding MAC addresses of systems they frequently communicate with in a table called ARP table. All the systems in the LAN maintain this table. The entries in the ARP cache table are generally short-lived and are updated every 15 to 20 minutes. Now let's get back to our topic. Can we say that one of the passive scan methods is just looking into the ARP table of a system, which is a network that we are scanning? Well, sure we can. Inside an ARP table, we see the IP addresses of some of the systems of the network and their corresponding MAC addresses. Let's see the ARP tables in 3 different platforms: Mac OS, Windows, and Debian Linux. We are in a Mac OS operating system first. Open the terminal first. Type terminal in the search box of the applications window, which brings you the terminal application. Typing ARP and hitting enter shows a small help for ARP command. If you want to see detailed help about the ARP command, you can use MAN command. Type MAN ARP and hit enter. You'll get detailed help. A parameter is used to display all current ARP table entries. But hold on, it says A is used to delete all entries as well. How can that be? Well, to delete an ARP table entry, you use D parameter. If you use this parameter with A parameter, you are able to delete all entries of ARP tables. I parameter is used to see the entries of a single interface. By default, ARP command tries to show the display addresses symbolically. To see the IP addresses instead of display names of the systems, you have to use N parameter, which means do not resolve names. Okay, press Q to quit the man page of the ARP command. Now type ARP-AN to see all the entries of the ARP table. Since Mac OS is a BSD-based operating system, the results of the ARP command is displayed in BSD style. Second machine is a Microsoft Windows 8. Let's open a command prompt first. I have a shortcut on my status bar, so I click it to start a command prompt. Alternatively, press Windows plus R buttons, open the dialog box, run Command, and hit Enter. If you type ARP in a Windows system, the help page of ARP command is displayed. Type ARP-A to see the entries of the ARP table. In my opinion, this display is more, human readable than BSD style. Now, although we're not interested in these at the moment, I would like to talk a little about the IP addresses that start with 224 to calm your curiosity. 224.0.0.22 is the multicast address for Internet Group Management Protocol. 224.0.0.252 is used by recent versions of Windows for Link Local Multicast Name Resolution, LLMNR, searching for local network computers. The third machine is our Kali, which is a Debian-based Linux operating system. Open the terminal window. If you type ARP and hit Enter, the ARP table entries are displayed in a human-readable format. As you see, systems are listed with a known domain name such as www.owaspbwa.com by default. ARP-H brings you a small help page. If you want a detailed help page, type man space ARP. In a Debian-based Linux system, -A parameter of ARP command is used to see the entries in BSD format, which we saw in Mac OS. -I is, again, to see the entries of a single interface. Okay, press Q to quit the man page. ARP-A displays ARP table entries in BSD format, and use N parameter to see the IP addresses instead of domain names of the systems. Wireshark is free, open source, and the world's foremost network packet analyzer, and it is the de facto standard across system and network administrators. Wireshark has the ability to listen and record traffic, as well as advanced filtering and reviewing options. We're not going to do a deep dive into Wireshark right now, since that's a subject of network layer attacks. So here, let's see a summary of the traffic and the systems related to the interfaces we listen. Let's go to Kali and start Wireshark. You can start Wireshark from the Applications menu or open a terminal window and type Wireshark to start the app. Don't worry about the ampersand and the and of the command. Putting an ampersand at the end of a command causes the shell to run the process in the background. It's sort of multitasking. You can have many processes running, but only one in the foreground at any given point. The process in the foreground is the process that appears to have locked up the terminal. Whatever. The first message is because we are a super user on Kali. No worries. Okay, the welcome page of Wireshark asks which interface we would like to listen to first. So let's have a look at the interfaces of our system. To look at the interfaces and to remember the IP address of Kali, open a terminal and type ifconfig. There are two result sets of the ifconfig command, eth0 and lo. eth0 is the first Ethernet interface. Additional Ethernet interfaces would be named eth1, eth2, etc. Here we have only one. Now lo is the loopback interface. This is a special network interface that the system uses to communicate with itself. eth0 is the interface that we're interested in at the moment. Double-click to open the eth0 on the main page of Wireshark to start capturing the packets passing through our Ethernet interface. Now to speed it up, let's create some network traffic. Open one of my virtual machines, OWASP BWA, and ping Kali. To stop ping command, press Ctrl-C, ifconfig, to learn the IP address of the machine. Now I go to another VM, Metasploit, and ping the last VM first. And then ping Kali. Here we have a lot of ICMP and ARP traffic at the moment. So let's generate some traffic. I open the browser in Kali and visit the website served by the OWASP BWA machine. And even more traffic. I visit nhs.uk, my favorite website. Okay, that's enough. Let's turn back to Wireshark. As you see, we have a lot of packets captured, and new packets arrive every second. ARP packets, TCP packets, TLS packets for HTTPS traffic, etc. Here we don't investigate the packets in detail. We want to learn about the systems which are interacting with us. So go to Statistics menu and select Conversations. There are 5 tabs in the Conversation window by default. And we're on the IPv4 tab at the moment. Here there are IP packets grouped by address A and address B. In each line, we see how many packets sent up to now, total size of the packets in bytes, number and size of the packets from A to B and from B to A, etc. There is traffic between 8.8.8.8 and my Kali. Now I know that 8.8.8.8 is the IP address of Google DNS, so I must have set the Google DNS as the DNS of my Kali. You know, I'd like to look at the network config. And yes, my DNS address is 8.8.8.8. In the Ethernet tab, we can see the MAC addresses of the systems. The addresses full of Fs mean that the packet is broadcasted. ARP requests are the examples for these kind of packets. In the TCP tab, we can see TCP packets grouped by the addresses and this time by ports as well, because a system may have different interactions with any other system. For example, Kali may have HTTP traffic through port 80, and at the same time, it may have an SSH connection through 22 as well. Same as TCP. Packets are grouped by IPs and ports in the UDP tab. Here we have learned a lot of live systems, IP addresses, and MAC addresses just listening to the traffic go through our network interface. If you'd like to investigate the traffic between the two machines, select the line, right-click. If you choose Apply as Filter from the menu, only these kinds of packets will be seen in Wireshark. I'll choose Find at this time. As you see, Automatic Query String is prepared. I can navigate between the packets by clicking the Find button. Go back to the conversation window. At the bottom right, there is a Conversation Types button. When you click on it, a lot of different protocols are listed. These selected 5 are the default selected protocols. You can add any protocol from the list. When you select one of them, a new tab is added to the conversation window. So have a look at what you see here. There are a lot of packets that Wireshark captures in seconds. There are some requests and responses for them, broadcasts and their replies, and etc., etc. There is an easier way to follow a stream, although this is very entertaining. The stream is a collection of packets that form a network conversation from the beginning to the end, just like your favorite story. So I'm in Kali now, and I captured the traffic just for a little bit. And while I was capturing, I visited a website to create some HTTP traffic. And here are the results: DNS packets, TCP packets, HTTP packets, etc. So I'll select an HTTP packet, and it's the GET request. Right-click, go to Follow on the submenu, and here you see the TCP stream and the HTTP stream options are both enabled. So that means we can follow either the TCP stream or the HTTP stream. So let's click HTTP stream. Now the client packets are red and the server packets are blue. The GET request by Kali, 200 OK response by OWASP BWA. Now this is a return page in HTML format. So you can scroll down and we'll see some of the other requests and the responses in the same stream. And perhaps you're beginning to see that when you click on a link in a website or visit a website by typing its URL, there might be several consecutive requests and responses that you don't even realize. But in actuality, you don't need to know them as the end user, but we're not your typical end users now, are we? So let's keep going. From the combo box at the left-hand side of the bottom of the stream window, you can filter the conversation from one side to another or vice versa. So at the right-hand side, there is another combo box where you can select the output format. Now when you close the stream window and go back to the main window of Wireshark, you can see that the stream filter is applied right here. So I'll remove the filter by clicking this cross icon. Now I see the entire captured traffic again. That is why filters exist. So in typical traffic capturing on a network interface, there are a lot of packets received from and delivered to all over the network and, well, the internet as well. So let's see how we can take a picture of that network. Let's go to Kali and start Wireshark. You can start Wireshark from the Applications menu or open a terminal window and type Wireshark to start the app. Don't worry about the ampersand and the and of the command. Putting an ampersand at the end of a command causes the shell to run the process in the background. It's sort of multitasking. You can have many processes running, but only one in the foreground at any given point. The process in the foreground is the process that appears to have locked up the terminal. Whatever. The first message is because we are a super user on Kali. No worries. Okay, the welcome page of Wireshark asks which interface we would like to listen to first. So let's have a look at the interfaces of our system. To look at the interfaces and to remember the IP address of Kali, open a terminal and type ifconfig. There are two result sets of the ifconfig command, eth0 and lo. eth0 is the first Ethernet interface. Additional Ethernet interfaces would be named ETH1, ETH2, etc. Here we have only one. Now, LO is the loopback interface. This is a special network interface that the system uses to communicate with itself. ETH0 is the interface that we're interested in at the moment. Double-click to open the ETH0 on the main page of Wireshark to start capturing the packets passing through our Ethernet interface. Now, to speed it up, let's create some network traffic. Open one of my virtual machines, OWASP BWA, and ping Kali. To stop ping command, press Ctrl-C, ifconfig, to learn the IP address of the machine. Now I go to another VM, Metasploit, and ping the last VM first. And then ping Kali. Here we have a lot of ICMP and ARP traffic at the moment. So let's generate some traffic. I open the browser in Kali and visit the website served by the OWASP BWA machine. And even more traffic. I visit nhs.uk, my favorite website. Okay, that's enough. Let's turn back to Wireshark. As you see, we have a lot of packets captured, and new packets arrive every second. ARP packets, TCP packets, TLS packets for HTTPS traffic, etc. Here we don't investigate the packets in detail. We want to learn about the systems which are interacting with us. So go to Statistics menu and select Conversations. There are 5 tabs in the Conversation window by default. And we're on the IPv4 tab at the moment. Here there are IP packets grouped by address A and address B. In each line, we see how many packets sent up to now, total size of the packets in bytes, number and size of the packets from A to B and from B to A, etc. There is traffic between 8.8.8.8 and my colleague. Now I know that 8.8.8.8 is the IP address of Google DNS, so I must have set the Google DNS as the DNS of my colleague. I'd like to look at the network config. And yes, my DNS address is 8.8.8.8. In the Ethernet tab, we can see the MAC addresses of the systems. The addresses full of Fs mean that the packet is broadcasted. ARP requests are the examples for these kind of packets. In the TCP tab, we can see TCP packets grouped by the addresses and this time by ports as well, because a system may have different interactions with any other system. For example, Kali may have HTTP traffic through port 80, and at the same time, it may have an SSH connection through 22 as well. Same as TCP. Packets are grouped by IPs and ports in the UDP tab. Here we have learned a lot of live systems, IP addresses, and MAC addresses just listening to the traffic go through our network interface. If you'd like to investigate the traffic between the two machines, select the line, right-click. If you choose Apply as Filter from the menu, only these kinds of packets will be seen in Wireshark. I'll choose Find at this time. As you see, Automatic Query String is prepared. I can navigate between the packets by clicking the Find button. Go back to the Conversation window. At the bottom right, there is a Conversation Types button. When you click on it, a lot of different protocols are listed. These selected 5 are the default selected protocols. You can add any protocol from the list. When you select one of them, a new tab is added to the Conversation window. Active Scanning. is done through sending multiple probe requests and recording the probe responses. Because passive scanners are limited to looking at existing traffic, they suffer in terms of overall completeness and accuracy. For example, a passive scanner can't detect an application that no one ever uses, and it can be fooled easily by a system intentionally spewing out misinformation and disinformation. The tools seen on the slide are a few examples of active scanning tools. In this course, we will examine the Nmap and Nessus tools in detail. HPing is an excellent command-line-oriented TCP/IP packet assembler analyzer. The interface is inspired by the ping 8 Unix command, but HPing isn't only able to send ICMP echo requests. It supports TCP, UDP, ICMP, and raw IP protocols, has a traceroute mode, the ability to send files between a covered channel, and many other features. So a subset of the stuff you can do using HPing: firewall testing, advanced port scanning, network testing using different protocols, TOS, fragmentation, manual path MTU discovery, advanced traceroute under all the supported protocols, remote OS fingerprinting, remote uptime guessing, and don't forget TCP/IP stacks auditing. HPing can also be useful to students that are learning TCP/IP. Although it's a packet analyzer tool, it's widely used for DOS, denial of service, tests, and attacks to create IP-spoofed packets and send them to the target system. Let's see how we can use the HPing command to scan the network simply. Go to Kali and open a terminal screen. HPing 3 is embedded into Kali and defined in the path, so you can use it anywhere, just typing the name of the command, HPing 3. Type hping3-h or hping3-help to see the detailed usage of the hping 3 command. Let's look at a few parameters important for scanning mode. Under the Mode title, we have a scan mode, and the help shows a sample usage of the mode as well. We'll use scan, or 8 parameter, to use HPing and scan mode. Under TCP UDP title, we have the parameters to set the flags of TCP or UDP packets. Well, you'll see the flags and meaning in this course in following lectures, so just see the HPing in action now. For example, uppercase S, or SYN parameter, is used to set the SYN flag of TCP or UDP packets. Let's prepare the HPing command to make a network scan. The first parameter is scan, to use HPing in scan mode. Here we should say in which ports we will scan. In this example, 0 to 500 means that the ports between 0 and 500 will be scanned. You can give a port range like this with a dash between the lower bound and the upper bound. Or you can give the ports one by one, separating them by a comma. Or you can use a combination of these two. Now I want to set the SYN flag of the packet, because all TCP connections start with a SYN packet. Well, again, we'll show you how a TCP handshake is made later on in the following lectures. Here comes the IP address to scan. Hit Enter to start the scan. Here we have the responding ports, and the flags column says what the reply is. We sent SYN packets and get SYN ACK packets. That means ports are accessible and open to us. Now let's make another scan. This time, I'll use uppercase X to make a Christmas scan. In the scan, push, urgent, and fin flags are set in the packet, which is not seen in regular traffic. Since the packets they received are not valid packets, they've dropped them and returned no response. Although it's not the subject of our course, because it's very common usage, I'd like to show you how to perform an IP-spoofed DOS, or denial of service attack, using the HPing tool. I'm going to attack my own server. First, I'll test if I can connect to the application. So open a terminal screen and ping the application www.owaspbwa.com. Okay, I have a connection through the application. Open a browser and visit the website. Here I click a few links to show the response time of the server. Oh, okay, it's really fast. It responds as soon as I click onto links. Now let's prepare the hping command to prepare a DOS attack. The first parameter of the command is -flood. You know what? Let's run hping3-help in another terminal screen to see the meanings of the parameters. Flood parameter is used to send packets as fast as possible. To make it a SYN flood attack, I set the SYN flag using -s parameter. When I send a SYN packet, since it's a legitimate TCP handshake starter, the server will try to respond to all the packets at the start of the TCP communication. So the server will be very, very busy. -v is to open verbose mode. That means we'd like to see the results of sent packets. The next parameter is rand source. This parameter will randomize the source IP addresses as if they are requested by different systems. So the attack is distributed denial of service now. And since the IP addresses are random, the victim doesn't know about you. Give the target domain as a last parameter. Oh, by the way, the order of the parameters is not important. Hit Enter to start the attack. Now, because we're in flood mode, no replies is shown. Let's try to click a few links to see the response time of the server while it's under attack. Click a link. It's waiting. It's obviously slowed down. Maybe our request will be timed out? So this is how a simple denial of service attack is performed. I'll stop the flood by stopping the run of the command using Control-C keys. As you see, in less than a minute, we sent more than 1 million SYN packets to the victim server. No packets received because we randomized the source IP addresses of the packets. That means the responses were sent to different IP addresses. This is why we didn't receive any packets. Since I stopped sending packets, the server is now responding in good time again. Now let's repeat the attack while Wireshark is running to see what's happening under the hood. Start Wireshark. Since we're using the ETH0 interface of Kali, I'll double-click the ETH0 on the home screen to start to listen to the traffic passing through the ETH0 interface. There's still some packets on the queue because of our previous attack. I restart capturing by pressing the green button at the upper left corner of Wireshark to clean the screen before the second attack. Continue without saving. Okay, Wireshark is running and clean. We're ready to repeat the attack. You can see the number of packets at the bottom of Wireshark. As you see, we sent hundreds of thousands of packets in seconds. So let's talk a little bit about the network and data link layer security. Why is it important, and how can we classify the network layer attacks, etc.? When the OSI model was introduced, there was no thinking of any type of security. Security just wasn't part of the design of either the OSI or TCP/IP models. Further, while there may be OSI layers, there are not necessarily protocols that correspond to them. You see, OSI was built to allow different layers to work without knowledge of each other. So any compromise in lower levels directly affects the higher levels. As a result, a system is as secure as its weakest link. In other words, security is as strong as the weakest link, right? So when it comes to networking, layer 2 is one of the weakest links. The protocols developed in the early years of the internet did not require a quality of service, QoS. For example, short delays in the protocols could be ignored. So the key principles of information security, CIA triad, confidentiality, integrity, and availability, were not integrated into the protocols, or they are really weak. So we can classify the network and data link layer attacks according to the effects of the attacks. Right? So these classes are denying the traffic between two hosts, sniffing or listening to the traffic, compromising the transferred data, and spoofing. So let's have a look at the network sniffing methods first. We're going to learn how to listen to the network traffic and how to use some tools such as TCP dump and Wireshark. During the penetration test, we listened to the network traffic for many good reasons. First of all, it's possible to obtain the clear text critical information, such as usernames, passwords, instant messages, emails, and all that. We can check to see if the scans work correctly. And some controls can be seen by listening to the network interface, such as if the scan parameters are set correctly, packets are properly exported from the network interface, and responses are received. Listening to the traffic, using passive scan methods, we can collect information about IP addresses, services running on server systems, and protocols and technologies used in network infrastructures, etc., etc. TCP dump is a free open source, very common, and fast packet analyzer that runs under the command line. It prints out a description of the contents of packets on a network interface that match the Boolean expression given as a parameter. TCP dump has a lot of filtering options. We'll discuss some of them in the next slide. It can be preferred to the other packet analyzers, such as Wireshark, because it's so fast. It also supports some of the most common network traffic capturing format, PCAP. You can save the results as raw ASCII text in a document as well. So have a look at this. These are some of the parameters you can use with the TCP dump command. D, or list interfaces, prints the list of the network interfaces available on the system and on which TCP dump can capture packets. I, or interface, listens in on the interface. If unspecified, TCP dump searches the system interface list for the lowest numbered configured interface, excluding loopback, which may turn out to be, for example, ETH0. N means do not convert addresses, that is, host addresses, port numbers, etc., to names. V produces verbose output when parsing and printing. The more V, the more details. W writes the raw packets to specified file rather than parsing and printing them out. R reads packets from the file which was created with the W option or by other tools that write PCAP or PCAPing files. A prints each packet in ASCII, handy for capturing web pages. When parsing and printing, in addition to printing the headers of each packet, capital X prints the data of each packet in hex and ASCII. This is very handy for analyzing new protocols. So if you use the X option, the data of each packet is printed in hex. In addition to these options, you can filter the results in several ways. If you would like to monitor a specific protocol, such as TCP, you can use its name as the filter. You can capture packets to or from an endpoint residing in the network using net filter, or use host filter to see the packets of a host as a source, destination, or either one. Use the port to filter TCP or UDP packets sent to or from a specified port. Use port range to listen to ports in any given range. Now, if you use the SRC option, you can see only the packets where the target system is the source of the packets. Similarly, DST is used to specify the destination system. So, of course, you can use more than one filter in a command and set up the relation using and or as logical operators. For example, host is 1.1.1.1 and port is 80. Now, before running several TCP dump commands, let's examine the fields of a typical TCP dump output row. The row shown in the slide is a TCP packet. The first field is the time when the packet arrived, with a timestamp as hour, minute, second, and, well, the fractions of a second. So the second field is a protocol running atop the link layer, in this case, IPv4. Now for IP packets, the third field is the IP address or host name of the host sending the packet, along with, for TCP and UDP packets, the source port. The packet on the slide came from port 80 of the system 172.16.99.139. Now the fourth field is the IP address or host name of the host receiving the packet, along with, for TCP and UDP packets, the destination port. Flags is the TCP segment flag. The packet on the slide doesn't have any flags set other than ACK. ACK is the acknowledgement number in the packet. TCP dump shows sequence and acknowledgement numbers relative to the initial sequence number by default. Win is the source host's TCP window, and you see the options field. Length is the length of the data in the TCP segment. The length here is 0, so that means that no data is exchanged yet. So that's enough for now. Let's see TCP dump in action. Time for hands-on. Okay, so before we talk about how to expand the sniffing space, let me explain the active network devices and the routers, hubs, and switches. Hub is commonly used to connect segments of a LAN, which is a local area network, and a hub contains multiple ports. When a packet arrives at one port, it is copied to the other ports so that all the segments of the LAN can see all of the packets. Hub acts as a common connection point for devices in a network. Now, switch operates at the data link layer, layer 2, and sometimes the network layer, which is layer 3 of the OSI reference model, and therefore support any packet protocol. Now, LANs that use switches to join segments are called switch LANs, or in the case of Ethernet networks, switched Ethernet LANs. In basically all networks, switch is a device that filters and forwards packets between LAN segments. A router is connected to at least two networks, commonly two LANs or WANs, which are the wide area networks, or a LAN and its ISP, which is the Internet Service Provider's network. Router is generally located at gateways, the places where two or more networks connect. Using headers and forwarding tables, router determines the best path for forwarding the packets. And in addition, the router also uses protocols such as ICMP, Internet Control Message Protocol, to communicate with each other and configures the best route between any two hosts. So, in a word, router forwards data packets along networks. Now let's compare the hub and the switch, since both of these two devices have similar roles on the network. Each serves as a central connection for all of your network equipment and handles a data type known as frames. Frames carry your data. When a frame is received, it is amplified and then transmitted onto the port of the destination PC, which is typically a personal computer. The big difference between a hub and a switch is in the method in which frames are being delivered. You got that? In a hub, a frame is passed along or broadcast to every one of its ports. It doesn't matter that the frame is only destined for one port. The hub has no way of distinguishing which port a frame should be sent to, right? So passing it along to every port ensures that it will reach its intended destination. Now, this places a lot of traffic on the network and can lead to poor network response times. You can only imagine, right? Besides, the frame is received by the unintended nodes, which could be hackers. And in a cybersecurity point of view, what about the confidentiality? And additionally, on a 10100 megabit per system hub, it must share its bandwidth with each and every one of its ports. So when only one PC is broadcasting, it will have access to the maximum available bandwidth. However, if there are multiple PCs broadcasting, then that bandwidth will need to be divided among all of those systems, which will degrade performance for everybody. So in comparison, a switch keeps a record of the MAC, which is the media access control address of all the devices connected to it. With this information, a switch can identify which system is sitting on which port. So when a frame is received, it knows exactly which port to be sent to, without significantly increasing network response times. And in addition, unlike a hub, a 10100 megabit per second switch will allocate a full 10100 megabits per second to each of its ports. So regardless of the number of PCs transmitting, users will always have access to the maximum amount of bandwidth. That's important. So it's for these reasons that a switch is considered to be, well, let's say a much better choice than a hub, right? Good. So switches make it difficult to sniff the network traffic. In the past, the traffic was being sent to all ports with the hub technology. With switches, the traffic is directed only to the specified port. So a network device only receives its own packets, not the others. So we need to use some techniques to sniff the traffic of the other devices then, huh? These are some of the techniques to expand the sniffing space. You thought it couldn't be done. So we'll talk about SPAN, switched port analyzer, or port mirroring. So that's a method of monitoring network traffic. With port mirroring enabled, the switch sends a copy of all network packets seen on one port or an entire VLAN to another port where the packet can be analyzed. Port mirroring is supported by almost all enterprise-class switches that I can think of. So in other words, managed switches. It allows a particular computer to see the network traffic, which is normally hidden from it. You can monitor the entire traffic sent from the switch by copying its uplink port. Now you have to have physical access and the admin privileges on that switch. So this method is often used to send the network traffic to the IDS, which is typically an intrusion detection system device. In a MAC address table overflow attack, also known as MAC flooding attack, within a very short time, the switch's MAC address table is full with fake MAC address and port mappings. Switch's MAC address table has only a limited amount of memory, and when that table is full, the switch cannot save any more MAC addresses in it. So once the switch's MAC address table is full and it can't save any more MAC addresses, it generally enters into a fail open mode, and it starts behaving like a network hub. Frames are flooded to all ports, similar to broadcast type of communication. So as an attacker in the network, you start to receive the frames of others. Address Resolution Protocol, ARP, or ARP, is a network layer protocol used for mapping a network address, such as an IPv4 address, to a physical address, such as a MAC address. A system asks for the owner of an IP address by sending an ARP request, and the owner of the IP address answers him with an ARP reply. What if the attacker replies first, before the owner of the IP? Once the attacker's MAC address is connected to an authentic IP address, the attacker will begin receiving any data that is intended for that IP address. This is the basic principle of ARP spoof attacks. ARP poisoning can be achieved because of the lack of authentication in the ARP protocol, so the attacker can send a spoofed ARP message onto the LAN. Would you like to make the attack much more powerful? I suspected as much. Then you've got to replace your MAC with the gateway. So every packet sent by the victim will be in your malicious hands. But we are ethical hackers, remember. Dynamic Host Configuration Protocol, DHCP, is a protocol used to provide automatic and central management for the distribution of IP addresses within a single network. It's also used to configure the proper subnet mask, default gateway, and DNS server information on the particular device. Now, similar to the other types of spoofing attacks, DHCP spoofing involves an attacker pretending to be someone else, in this case, acting as the legitimate DHCP server. Since DHCP is used to provide addressing and other information to clients, losing control of this part of the network can be very dangerous. In DHCP spoofing attacks, the attacker places a rogue DHCP server on the network, and as clients are turned on and request an address, the server with the fastest response is used. If the device receives a response from the rogue server first, the rogue server can assign any address as well as control which device it uses as a gateway. So a well-designed attack can collect traffic from local hosts to a rogue server that logs all traffic and then forwards out the traffic to the correct gateway or to the device. So this action would be almost transparent. Thus, the attacker can steal information almost invisibly. The foundation of a Mac flood is to make a switch behave like a hub. As I mentioned before, a hub sends the packet it receives to all of its ports. However, a switch sends the packet only to the target system. So if we can make the switch behave like a hub, then it would send the packet to all of its ports, and I could listen to the traffic even though I'm not the target. In a Mac flooding attack, within a very short time, the switch's MAC address table is full with fake MAC address and port mappings. Once the switch's MAC address table is full and it cannot save any more MAC addresses, it generally enters into a fail open mode and it starts behaving like a network hub. Ethernet switches uses MAC address tables to determine where to forward traffic on a LAN. So let's go step by step to understand how the MAC address table is built and used by an Ethernet switch to help traffic move along the path to its destination. Now suppose that all of the devices connected to the switch are powered on but have not sent any traffic yet. In this case, the MAC address table of the switch would be empty. Now suppose computer A wants to send traffic to the server. It prepares an Ethernet frame, and it sends it off toward the switch. The first thing the switch would do when receiving the traffic is to create a new entry in its MAC address table for computer A's MAC address. Makes sense? The switch then performs a lookup on its MAC address table to determine whether it knows which port to send the traffic to. And since no matching entries exist in the switch's table, it floods the frame out all of its interfaces except the receiving port. Because the frame was sent out to all the switch's other ports, it is received by the target server as well. Then the server sends a new frame back toward the switch. The other systems which receive the frame do nothing. The switch receives the frame and creates a new entry in its MAC address table for the server's MAC address. It then performs a lookup of its MAC address table to determine whether it knows which port to send the server's traffic to, and in this case, it does. So it sends the return traffic out only on the port of computer A, without flooding. So this process repeats as devices continue to send traffic to each other. An important detail to remember is that the MAC address table timeout is typically short. So for example, default timeout duration of Cisco switches is 5 minutes. So an entry is left in the table itself only for that specified amount of time before the timeout expires and the entry is removed from the table. Let's look at the switching mechanism with a cybersecurity point of view. The mechanism has two weaknesses in it. First, When the target MAC address is not in the MAC address table, the frames are flooded out of all the ports, so unintended systems on the network are capable of sniffing these frames. The second weakness is that when the MAC address table is full, no new record is accepted. So what if I fill the table by announcing thousands of fake MAC addresses from a port of the switch? Most of the switches start to behave like a network hub in such a situation, which means they send each frame to all of the ports. So look at the page seen in the slide. This is the manual page of the macof command. Macof is a command line tool mainly used to flood the switch on a local network with random MAC addresses. So as I mentioned before, when the switch receives a frame, it creates a new entry in its MAC address table for these MAC addresses. Once the switch's MAC address table is full, and it cannot save any more MAC addresses, it generally enters into a fail open mode, and it starts behaving like a network hub. So let's see macof command in action. So here's a network that I created in GNS3. Well, the IP addresses are different from the one that I created in the previous lectures, but not to worry, it's completely identical with that network. So in addition, I've added some other VMware VMs, OWASP, Broken Web Applications, and Metasploitable in the same way with Kali. Now, just a little word of caution, while you're adding a VMware VM to a GNS3 network, do not forget to create a new custom network mode, such as VMnet2, because all VMs need a separate custom network mode. Remember that. Okay, so now I'll go to Kali. Since Kali is a part of the GNS3 network, its network settings is custom, so it's not in NAT mode right now. Have a look at the IP address using ifconfig. Okay, so it's in 192.168.10.0.24 IP block. So now check the entire network. I go over to the other VMs and look at the interface configurations. These are the IP addresses of all the VMs. Now go to Kali and ping them. The results are pretty good. We got the reply packets for ping requests. So now I open another terminal screen and scan these two VMs and see the open ports and running services. So I'll simply use the nmap command with the IP address only. So it'll be a SYN scan, and the top 1,000 ports will be scanned. Here are the results. 10.11 has 9 open ports, and 10.12 has 23. And as you see here, telnet port of the 192.168.10.12 is open. So let's go to the VMs. 10.12 is Metasploitable, and 10.11 is OWASP BWA. Now, we know the telnet service is running on Metasploitable. So to create some traffic and let the switch fill the MAC address table, I'll start up a telnet connection from OWASP BWA to Metasploitable. Type telnet and the IP address of Metasploitable. Enter the username and password, which are already given as a welcome message here. And we got the session. Okay, so we can exit now. Now I'll go to the console of the switch and type show MAC address table dynamic to see the dynamic records of the MAC address table. Now here there are 6 port and MAC mappings for now. Run the command again, and now we have 2 rows. So it seems, by the look of this, that the MAC address table aging is 10 or 15 seconds. Okay, you ready for this? This is the time of MAC flooding. So now I'm in a terminal screen on Kali. Have a look at the manual of macof command first. So type man macof and hit enter. Macof is a tool that's used to flood the local network with random MAC addresses. And here are the options. I, to identify the network interface to attack. N, to specify the number of packets to send. D, to specify the destination system's IP address, etc. So let's create the command. Of course, the first command I'll send is macof. I, the interface that's used to attack, will type that in as eth0. D, the destination, the ether switch router. Now we're ready to run the command, so hit enter. And the Mac flood started, and macof sends tens of packets in seconds. Now let me go to the ether switch router console and look at the dynamic MAC address table again. You can call the last command by using the up arrow key. And as you see, there are a lot of rows for our fast Ethernet 1.0 port, which is used for Kali. So while macof is running, let's run Wireshark and try to listen in to the traffic on the telnet of Kali's own network interface. Now to see only the telnet traffic, type telnet in the filter box and click the blue button next to the box. Okay, no telnet traffic for now. Now I go back to the OWASP BWA VM and telnet to the Metasploit VM again. Telnet, the IP address of Metasploitable, username and password. Run a command. Okay. So back to Kali. You see the telnet traffic here. Kali is neither the source of the traffic nor the destination. It receives the telnet traffic. Now, this is a typical in hub behavior to send packets to each node, so we can say that our switch is behaving like a hub now, just like we predicted. So let's go ahead and stop Wireshark and the macof command using Control-C keys. You can do that. These are the telnet packets. Since telnet is a clear text protocol by default, we can see the payload as well as the metadata. We can see every character in a different packet. So select one of them. Right-click, follow, and select TCP stream. So the red characters here are client packets. The blue characters are the server packets. Here's a credential, username, and password. So I bet you're hoping to learn how to prevent MAC flooding attacks, and you've come to the right place. To prevent the MAC flooding attacks, network operators usually rely on the presence of one or more features in their network equipment. With a feature often called port security by vendors, many advanced switches can be configured to limit the number of MAC addresses that can be learned on ports connected to end stations. Many vendors allow discovered MAC addresses to be authenticated against an authentication, authorization, and accounting or AAA server, and subsequently filtered. Implementations of IEEE 802.1x suites often allow packet filtering rules to be installed explicitly by a AAA server based on dynamically learned information about clients, including the MAC address. Security features to prevent ARP spoofing or IP address spoofing, in some cases, may also perform additional MAC address filtering on unicast packets. However, this is an implementation-dependent side effect. An ARP spoof is performed replying to an ARP request before the real owner of the IP address. Because of the lack of authentication mechanisms in ARP protocol, you're able to set yourself as the owner of the IP in the source machine's ARP table. Okay, to understand the ARP spoof or ARP cache poisoning attack, let's remember the ARP protocol and its principles once again. Address Resolution Protocol, ARP, is a network layer protocol used for mapping a network address such as an IPv4 address to a physical address such as a MAC address. To simulate how the ARP mechanism works, we have a small network in the slide, a switch on top, and 3 computers connected to it. Computer A wants to talk to Computer C. It puts an ARP request onto the wire, which happens to be broadcast. Essentially what it's saying is, who has computer C's MAC address? Of course, because it's a broadcast, every system on the network hears it. Does everybody respond? Well, what happens is that B hears that A is looking for the MAC address of computer C. B knows that it's not computer C and therefore does not respond to the broadcast. The broadcast, the ARP request, goes out to every system, but the only system that will reply is computer C with an ARP reply. In other words, computer A says, who has the MAC address of computer C? And although all the workstations hear the question, only C replies and says, I've got the MAC address of computer C, and this is what it is. So the ARP reply sends back the MAC address to computer A, and each of these machines start building an ARP table. These are how ARP requests and responses look in Wireshark. The first packet is an ARP request. As you see, it is broadcast. And the second packet is an ARP reply. The owner of the IP 207 answers with its MAC address. As you see, ARP request is broadcast throughout the network, and the first reply is trusted and accepted. Okay, so we have already seen the routine of the ARP protocol. Computer A sends an ARP request. The request is broadcast. The owner of the IP replies with an ARP reply, and both sides update their ARP tables. Now we have an attacker in the network. Okay, so this is how the ARP spoof attack works. Computer A wants to talk to computer C. If the MAC address table of computer C is not in the ARP table of computer A, it puts an ARP request into the wire, which happens to be broadcast. This is the point where all the computers on the network get the ARP request. So although it's not his IP address, the attacker replies the ARP request before the real owner. In this ARP reply, the attacker puts his own MAC address corresponding to the target IP address. Computer A receives the ARP reply and stores the address pair in its ARP table, and communication takes place. Oh yes, there's plenty more to do. There are several tools to perform an ARP spoof attack, such as ARP spoof, the command line tool which is embedded in Kali. But we're going to use EtterCap for the demonstration of the ARP spoof attack. EtterCap is a free and open source network security tool for man-in-the-middle attacks on LAN. It works by putting the network interface into promiscuous mode and by ARP poisoning the target machines. Thereby, it can act as a man-in-the-middle and unleash various attacks on the victims. EtterCap has both a command line interface version and a graphical user interface version. Let's see them both in action. First, let me show you the command line version of EtterCap. So this is my network created in GNS3. I have a Kali, an OWASP BWA, and a Metasploitable VM in the network. So use ifconfig inside the VMs to check the IP addresses and the other interface configurations as well. So ping each other to be sure that they can communicate. Okay. Now I go to Kali, open a terminal screen, and do the same here. Check the interface configuration and ping other VMs. Yep, everything's okay. So let's look at the ARP table of Metasploitable. Type ARP-N and press Enter. So currently there are two records in the ARP table of Metasploitable, one for Kali and one for OWASP BWA. Now let me show you something. If you want to perform an ARP spoof attack, you should enable IP forwarding in your attacker system so that the packets will not end on your attacker system and be forwarded to the destination system. Otherwise, you'll block the traffic between the victim and the spoofed system. Check that out. So the IP address is managed by a variable IP forward, like in Kali. And to look at the file content, type cat/proc/sys/net/IPv4/IP forward and press enter. Its value is 0. So to enable it, it has to be 1. So I'll change it. You can open the file with a text editor and change the value, but here I'll just simply use the echo command for this purpose. Echo 1 greater than sign the entire file name. So check the file again. And yes, its value is now 1. Now, please note that EtherCap enables IP forwarding automatically, even though you don't enable it manually. All right, I want you to know what's happening behind the scenes, so to speak. All right, so now's the time of the attack. Before creating the command, let's see the manual of EtherCap. So type man EtherCap and press enter. So here's the short definition and the long description. Targets, options, M for man in the middle, MIT-M attack. So these are the MIT-M attack types. ARP is at the first line, and the others, ICMP, DHCP, etc. And here are the user interface options. T for the text-only interface. Anyway, let's just create the command. So first, the command itself, EtherCap. I, the interface, either 0. T for the text-only interface type. M to make it a MIT-M attack. And select the MIT-M attack type, ARP, column, remote. So the first IP specifies the IP address which will be spoofed. And the second IP address is the victim system. So that means there will be a row in the Metasploitable's ARP table with a Kali's MAC address and OWASP BWA's IP address. And that means when Metasploitable wants to send a packet to OWASP BWA, it will be sent to Kali instead, right? And with the help of IP forwarding, the packet will arrive at OWASP BWA finally. Now, please don't forget to use these slashes at the beginning and end of each IP address. The command is ready to run. So let's see what it does. Hit enter. And here's a summary of the attack, the victims, interface type, etc. Now I'll go to Metasploitable, ARP N, to see the ARP table again. And as you can see here, the first record is for Kali. So please look at the MAC address. And the second record is for OWASP BWA, but with the attacker's MAC address. Any packet sent from Metasploitable to OWASP BWA will visit Kali now. So let's create a telnet connection to port 80 of OWASP BWA. Type telnet OWASP BWA IP and the port 80. Now hit enter. Type get/http/1.0 and press enter twice. And here is the HTTP response, the main page of OWASP BWA. Now let's go back to Kali and see what happens. So these are all the TCP packets sent from Metasploitable to OWASP BWA. ACK packet, FIN packet, and scroll up a bit, and here's the telnet connection results. HTTP response. Keep going up. We can find some other critical data here too. And here's some credentials, for example. In the terminal screen where EtherCap is running, you can use Control-C to end the attack. So there it is, it stopped. Now go back to Metasploitable and look at the ARP table again. Now the IP address of OWASP BWA is matched with the correct MAC address. Now, you might remember what I told you before well, I hope you remember everything that I told you before. But, in particular, EtterCap has a graphical user interface as well. So let's have a look at EtterCap's GUI right now. Again, we're in Kali. Click Show Applications menu item and type EtterCap. And here you go, you'll find the EtterCap GUI app. So these are both EtterCap GUI apps. You can just simply click one of them. I want to show you, though, another way to start the app. From the upper left corner, Applications, go to Sniffing Spoofing Tools, and select EtterCap GUI. Okay, so here we are at the main panel of the EtterCap GUI. We'd better check the network, so I'll open up a terminal screen and ping the other VMs, Metasploitable and OWASP BWA. Yeah, everything looks okay. So go to the Sniff menu in EtterCap and select Unified Sniffing. Asking for input interface, ETH0 is good. Click OK. If you look at the EtterCap menu, it's totally different now. So go to Hosts and select Scan for Hosts. It's a kind of a ping scan to find out the devices of the network. It found 5 devices and added them to the hosts list. So go back to Hosts again, and now select Hosts Lists. And here's a list. Very nice. Works well. 192.168.10.11 is OWASP BWA. So this is the system that will spoof. So select it and click Add to Target 2. So 192.168.10.12 is Metasploitable. That's our victim. So we'll change its ARP table. Select it and click Add to Target 1. I think now we're ready to attack. What do you think? All right, so let's go to MIT-M and click ARP Poisoning. Okay, check the Sniff Remote Connections option and click OK. And the final step, go to Start and select Start Sniffing. So the attack has begun. Let's go to Metasploitable and see the attack result. To see the ARP table, type ARP-N and press Enter. The first row is for OWASP BWA, but the MAC address is Kali's MAC. To show it, now I'll ping Kali to create the ARP record. Run the ARP command again, and now I have another row for Kali. And both Kali and OWASP BWA have the same MAC address. Okay, you know the rest. The packets will be sent to Kali instead of OWASP BWA, so if you'd like, you can open Wireshark and collect the fruits of your labor. Enjoy it. Now, similar to the other types of spoofing attacks, Dynamic Host Configuration Protocol, DHCP spoofing, involves an attacker pretending to be someone else. In this case, acting as a legitimate DHCP server. Since DHCP is used on most networks to provide addressing and other common information to clients, losing control of this part of the network can be dangerous. Dynamic Host Configuration Protocol, DHCP. Now, it's a protocol used to provide automatic and central management for the distribution of IP addresses within a network. It's also used to configure the proper subnet mask, default gateway, and DNS server information on the device. In most homes and small businesses, the router acts as the DHCP server. In large networks, a single computer might act as a DHCP server. In short, the process goes like this. The device, the client, requests an IP address from a router, the host, after which the host assigns an available IP address to allow the client to communicate on the network. So let's look at some of the advantages of using DHCP. A computer or any other device that connects to a network, local or internet, must be properly configured to communicate on that network. Makes sense? Since DHCP allows that configuration to happen automatically, it's used in almost every device that connects to a network, including computers, switches, smartphones, gaming consoles, you name it. Now, because of this dynamic IP address assignment, there's less of a chance that two devices will have the same IP address, which is very easy to run into when using manually assigned static IP addresses. Using DHCP also makes a network much easier to manage. From an administrative point of view, every device on the network can get an IP address with nothing more than their default network settings, which is set up to obtain an address automatically. So that's easy, gives them nothing to call the help desk about. The only other alternative is to manually assign addresses to each and every device on the network. You're not getting paid enough to do that. So because these devices can get an IP address automatically, they can move freely from one network to another, given that they're all set up with DHCP, and receive an IP address automatically, which is super helpful with mobile devices. Now, as a cybersecurity expert, you should know one more thing about the DHCP mechanism. The first device which replies to a DHCP discover request decides the configuration of the client. There is not any mechanism to authenticate the DHCP server. Similarly, a DHCP server tries to reply to all the DHCP requests, and again, there is no authentication mechanism for the clients who request an IP. You get it? I think you do. What if a hacker replies before the real DHCP? Or what if a client sends a lot of DHCP discovery requests by changing the MAC address each time? So let's have a look to see how a DHCP mechanism works in detail. Once a device is turned on and connected to a network that has a DHCP server, it will send a request to the server called a DHCP discover request. After the discover packet reaches the DHCP server, the server attempts to hold on to an IP address that the device can use and then offers a client the address with a DHCP offer packet. Once the offer has been made for the chosen IP address, the device responds to the DHCP server with a DHCP request packet to accept it. After which, the server sends an ACK packet that's used to confirm that the device has that specific IP address and to define the amount of time that the device can use the address before getting a new one. If the server decides that the device cannot have the IP address, it will send a NAC. Let's see the DHCP server mechanism in Wireshark. So Wireshark is already embedded into Kali and it's ready to use. In addition, I'd also like to show you how to download and install it in a Windows system. So right now I'm in a Windows 8 system. Open the internet browser and search for Wireshark for Windows, using those as the keywords. First link is the download page of wireshark.org. So let's click it. My Windows is 64-bit, so I'll download the 64-bit, which is the latest stable version. Click it and save the installer. Now it takes less than a minute unless your connection is a mess. You might want to look into that. Just kidding. Click to run it. The setup wizard opens. Okay, so simply it's a next, finish installation. No need to change anything. Wait until the installation finishes. Okay, so check this to run Wireshark now and click Finish. And welcome to the Wireshark and Windows interface. So now I will show you the DHCP mechanism in Wireshark. So let's run Wireshark, and you can see that it's listing the packets received by ETH0. So to demonstrate the DHCP mechanism, we need to ask for an IP address over at the DHCP server. From the bottom right corner, right-click to the network icon and select Open Network and Sharing Center. Click Ethernet 0 and then Properties. You'll have to scroll down a little bit and double-click IP version 4. And as you see here, the IP address is manually set for my Windows 8. So to start a DHCP request, I'll choose Obtain an IP address and DNS server address automatically. Those are my options. Now, before I click OK, I'll go to Wireshark and restart capturing by clicking the green button on the toolbar. So now Wireshark Windows will be cleaned. Continue without saving. So now go to the network status window and click OK. And we can close all the networking windows. So Wireshark captured the packets. Well, it's still capturing, but let's go to the top of the list to find the DHCP packets. So here the DHCP Discover packet is right here at the top of the list. When we look at the ports in the UDP header, we see that the port 68 is used to send DHCP Discover packets. So let's go back to the filter box and type UDP port equals 68. And now we have the DHCP packets only. So the first packet is DHCP Discover. And as I mentioned before, it's broadcast. Source IP is all zeros because we don't have an IP address at the moment. Destination IP is all ones, 255.255.255.255 because it's a broadcast packet. And right here is Bootstrap Protocol, which is an application layer protocol used by DHCP mechanisms. The second packet is a DHCP offer packet sent by the DHCP server, 172.16.99.254 to the Windows system. The destination IP is 172.16.99.233, which is offered to the DHCP server. So in here, the destination MAC address is important. That's what's going to be targeted according to the MAC address. So as you see, the destination MAC address of the DHCP offer packet is the same as the source MAC address of the DHCP Discover packet. Now the third packet is the DHCP request sent by the Windows system. It's still a broadcast packet and the source IP is still all zeros. The message is request and the requested IP address is an option 50. So if you expand it, you see the requested IP address. And it's the same as the offered IP address, 172.16.99.223. The last packet is DHCP ACK, sent by the DHCP server to the Windows system. This packet completes the DHCP mechanism successfully. So from now on, the IP address of our Windows system is 172.16.99.223.